Swayam Prabha. Digital India. Educated India.
Now we have to continue the tau of n, sigma of n, s of n, followed with phi of n, lambda of n and b of n, right. Let n be a positive integer, then Euler-Totian function is phi of n is defined by the number of positive integer k less than n which are relatively prime to n. So, number of positive integer k and which is less than n, and that should be relatively prime to n. For example, you have to 3, say what are all the positive integers relatively prime to 3. Therefore, 1 is for example, you start with this n equal to 1 you take it, n equal to 1 you take it. So, what are all the relatively prime to 1 is 1 only, therefore, phi of 1 equal to 1. So, 1 will come. If you take n equal to 2, then what are all the relatively prime to 2 is only 1. Therefore, we have what 1, therefore 1. 3 you take it 1 and 3, therefore, we have what 2 also relatively prime to 3, because the GCD of 2 and 3 is 1, the GCD of 1 and 3 is 1, totally it comes 2, this and this 2. So, if you take 4 and then what are all relatively prime to 4 is 1, 3. So, totally 2. So, 2 will come. You take 5, relatively prime to 5 is 1, 2, 3 and 4. See, totally 1, 2, 3, 4. So, 4 term. And you take a 6, what are relatively prime to 6 is 1, 2 does not come, 3 does not come, 4 does not come, 5 will come, that is all, only 2. So, 2. You take a 7 and then what are all relatively prime to 7? 1, 2, 3, 4, 5, 6, right. Totally 6 term will come, yes, 6 term coming. So, like that you have to do for relatively prime to 10. So, 1, 2 does not come, 3 will come, 4 does not come, because the greatest common is not equal to 1, more than number will come, 5 will come, 6 does not come, 7 will come, 8 does not come, 5 does not come, 7 will come, 9 will come, 10 will come. So, totally 1, 2, 3, 4. So, 4 will come. Now, you take 100, 40 terms will come, 101, 100 terms will come, 102 having 32 terms will come, 103, 102 terms will come. Now, that is the meaning of summation 1 less than or equal to k less than n 1. So, this is the general form of the notation of phi of n. Now, you see if n is a prime, right. So, that number minus 1 is a what phi of n will come. So, take 2, 3, 5, right. You take this point, this one prime, and then 101 is a prime, 103 is a prime. So, 2 minus 1 equal to 1, so coming. So, 3 minus 1 equal to 2, here 5 minus 1 equal to 4, here 7 minus 1 equal to 6, here 101 minus 1 equal to 100, 103 minus 1 equal to 1, 2. So, like that we can write phi of n. So, based on that we have a lemma for any positive integer n, summation d divides n phi of d equal to n. So, number of positive divisors are n, you have to find out this. Next theorem, let n be a positive integer, then Euler-Totian function phi is a multiplicative, and then GCD of m comma n is 1. Then phi of m n equal to phi of m into phi of n. You take 2 and 3. What is phi of 2? The GCD of this number is 1, and phi of 2 is 2 minus 1 is 1. Phi of 3 is 3 minus 1 is 2. Now, phi of 6 you take it. So, we have what is phi of 6? So, phi of 6 is 2, right. So, you keep it in mind, right. So, that what phi of 6 is 2, right. So, phi of 6 can be written as phi of 2 into 3, which is equal to phi of 2 into phi of 3, which is equal to phi of 2. What is phi of 2? Is 1, phi of 3 is 2. So, net value is 2. So, 2 will come. So, this way we can express phi of mn equal to phi of m into phi of n. Similarly, if you take any positive integer 6, n equal to 6, and summation 2 divides 6, right, then phi of 2 should be what? N. Say for example, you have to write 2 divides 6 is what? 6 by 2 is 3, right. So, we have what? N equal to 6 is summation of all these things you have to do. What are all the divisors of 6, right? One is 2 divides 6, another is 3 divides 6, and 1 divides 6. So, these are all the things, and totally you have to do only 2 will come. So, phi of 2 is equal to 1, and then n phi of 3 equal to 2, and then phi of 6 equal to 2, and then phi of 1 equal to 1, addition them, so that 6 will come. That is the first one. So, next what you have to do is, if n is a prime, n is equal to 5, say p. So, this is p, right. So, phi of 5 is equal to 5 minus 1 equal to 4. Yes, it works. Conversely, if p is a positive integer, then phi of p equal to p minus 1, then p is a prime. And if n is a prime, power of p per alpha with alpha greater than 1, then phi of p per alpha equal to p per alpha minus p per alpha minus 1. If n is a composite and has a standard prime factorization form, then phi of n equal to p1 power alpha 1 into 1 minus p1, p2 power alpha 2 into 1 minus p2, and so on, pk power alpha k into 1 minus pk, and then how many terms? P1 power alpha 1 into P2 power alpha 2, and so on, pk alpha k, call it as n, and the rest of them denote as a product of p of n into 1 minus p. So, if n equal to 6, then this can be written as 6 into product of p divides 6, that is, which one is a number this, and then 1 minus p. So, 2 and 3 is divides, therefore, 2 divides 6 into 1 minus 1 by 2 into 1 minus 1 by 3, and then into 6, it pakka works. So, 6 into by 6 is p of n, corresponding value will come, right, provided n is a composite number. So, the proof is, if g of n equal to n is a multiplicative and n equal to summation d divides n phi of n, it follows from the theorem that phi is a function of multiplicative. If n is a prime and then 1 to n minus 1 are relatively prime to n. So, it follows that by definition of function phi of n equal to n minus 1 term. Conversely, if n is not a prime, then n has a divisor d such that greatest common divisor of d comma n not equal to 1. Therefore, at least one of the positive integer less than n which is not relatively prime to n, and hence phi of n less than or equal to n minus 2. And note that the GCD of n comma p power alpha is 1 if and only if definitely p does not divide n. There are exactly p power alpha minus 1 of integer between 1 and p power alpha is divisible by p. Therefore, the namely p, 2p, 3p and so on, p power alpha minus 1 into p can be written as the set of 1, 2 and so on p power alpha contain exactly p power alpha minus p power alpha minus 1 integer. Therefore, they are relatively prime to p power alpha. So, by definition of phi function, p power p power alpha is equal to p power alpha minus p power alpha minus 1. So, p power what 2 square is equal to what 2 power 2 minus 2 power 2 minus 1 which is equal to 4 minus 2 power 1 which is equal to 2. P of 4 is 2 and definitely it works. So, this way we can write what the proof of the function. Now, we use the mathematical induction on k and a number of distinct primes factors. By part 3 of this theorem, the result is true for k equal to 1. Suppose the result is true for k equal to I, then the GCD of p1 power alpha 1 minus 1 into p2 power alpha 2 and so on pi power alpha I into pi plus 1 alpha I plus 1 equal to 1. By multiplicative function, we can product into two terms of up to this and then separately this, so that product them it is true phi of mn equal to phi of m into phi of n. Therefore, this is nothing but this term, and phi of pi plus 1 to alpha I plus 1 is subtract them p suffix I plus 1 alpha I minus 1 alpha I plus 1 to minus p suffix I plus 1 to alpha I plus 1 minus 1. So, each term we can have like this, and then we can separate into the previous theorem. So, we can do the p1 power alpha 1 minus p1 power alpha 1 minus 1, p2 power alpha 2 minus p2 power alpha 2 minus 1 and so on, pi power alpha I in minus pi power alpha I minus 1 into p suffix I plus 1 of this last term. Now, every term we have to multiply and then take common of the first term p1 power alpha 1, so that p1 power alpha 1 into 1 minus of this term will come. Similarly, for second term p2 power alpha 2 take common and then this, and the last term pi plus 1 suffix and power alpha I plus 1 take it common, so that will come. So, all these things multiply separately of p1 power alpha 1 into p2 power alpha 2 and so on p suffix I plus 1 into alpha suffix I plus 1 is called as n, and then rest of them written like this. So, this theorem is holds good for up to alpha I plus 1. Now, we are going to discuss the Carmichael lambda function, where lambda n is defined as follows. For lambda of p is also equal to phi of p, which is equal to p minus 1 for prime p, and lambda of p power alpha is phi into phi of p power alpha, right. For p is equal to 2 and alpha is less than or equal to 2, and for p is greater than or equal to 3 also it is holds good. Say if p equal to 2, then phi of 2 equal to 2 minus 1 is 1 will come. If if alpha equal to 2 and p equal to 2, then phi power 2 square equal to phi power 4, and phi power 4 is what? The number of function of p power 4 is corresponding what are all the devices, right. So, this is p power p of 4 is 2, therefore 2 will come. So, phi of 4 equal to 2 will come. So, like that we can extend to what Carmichael number to lambda function. So, lambda of 2 power alpha equal to 1 by 2 into phi of 2 power alpha, where alpha is greater than or equal to 3. Similarly, lambda of n equal to LCM of lambda into p1 power alpha 1 into lambda into p2 power alpha 2 and so on, lambda into pk power alpha k, where n equal to the product of prime powers. Now, we will go to the each number using these ideas. See, you take n equal to 1. So, what is lambda 1? Lambda 1 is a prime, therefore, so for prime p it is true, only 1. Okay. So, it is holds good for phi of 1 and 1 only will come, and for x you take p equal to 2, right, and then lambda 2 and phi of 2 equal to 2 minus 1, which is equal to 1, this works. If you take p equal to 2 and alpha equal to 2, and then lambda of 2 square is equal to phi of 2 square, which is equal to phi of 4. Phi of 4 is 2, therefore, lambda of 4 is also 2. So, it holds good. And if p is greater than or equal to 3, mean p equal to 4 you start. So, p equal to 4, then lambda of 4 which is equal to and alpha is equal to some number, you take it what 1 you take it, then lambda of this one is phi power 4 which is equal to phi of 2 square, already we done it. So, this holds good. If you have lambda of 2 power alpha, alpha is greater than or equal to 3, or suppose you take alpha equal to 3, what happened, lambda power lambda of 2 power 3 is 8. So, lambda lambda is 8, then what you have to do, it becomes you have to do the rule is 1 by 2 into phi of 2 power alpha, right. So, 1 by 2 into phi of 2 power 3. So, 1 by 2 into phi of 8. So, so lambda power 4 is lambda power 8 is 4, therefore 1 by 2 into 4, which is equal to 2. So, lambda 8 is 2, beautifully coming. Like that you have to do with all these ideas. Now, we have the last one. So, lambda of n is what, some 10 you take it, n equal to 10. So, what happened, n can be expressed as a product of prime. So, 2 into 5. Now, what you have to do? So, lambda of 10 we can write least common multiple of lambda of 2 power 1 into lambda of 5 power 1. Here alpha 1 equal to 1 and alpha 2 equal to 1. So, LCM of lambda of 2, what is lambda of 2? 1, lambda of 5, 4. So, LCM of 1 into 4 is what? 4. So, LCM of 4 is what? 4. Therefore, lambda of 10 equal to 4. Yes, beautifully coming. Like that you have to work with a Carmichael lambda function. Next, let us go with one example. You take n equal to 65, 520. It can be expressed as product of prime powers, right? 2 power 4 into 3 square into 5 into 7 into 13, and a equal to 11, you take it. Then the GCD of 65, 520, 11 is 1, right? It is working. We have phi of 65, 520 is nothing but what? That is 4, that is what? Phi of this one is nothing but 8 into 6 into 4 into 6 into 12. That becomes what? 13824. Whereas lambda of 65, 520 is LCM of what? 4 and then what? LCM of 4, 6, 4, 6 and 12, because 8 can be written as 4 into 2. Therefore, among these which one is LCM? 12. So, that is called as lambda of n. So, lambda of 65, 520 is 12 and phi of this number is 13, 824. So, that is a difference. So, in this way we can define the Mobius mu function, mu of n defined as follows: mu of n equal to 1 if n equal to 1, if n contains square factor it becomes 0, if n is a product of primes, distinct primes, then corresponding mu of n equal to minus 1 whole power k. For example, if you take n equal to 1, so obvious it is 1 will come. So, n is not equal to 1, then n equal to 2 you take it, 2 you take it, therefore, mu of 2 is nothing but here k distinct primes, right. So, minus 1 here k is equal to 1, therefore, what mu of minus 1 whole power 1 which is equal to minus 1. So, minus 1 coming. If n equal to 3 you take it. So, here mu of 3 equal to it is not 1, therefore, it is also not a square, therefore, it is a product of primes 3 power 1, here k equal to 1, therefore, minus 1 whole power 1 equal to minus 1 is coming. If n equal to 4 you take it, so this can be written as 2 square, therefore, it contain square factor, therefore, mu of 4 equal to mu of 2 square, therefore, it becomes 0, therefore, 0 value. So, like that you take n equal to 8 can be written as 2 power 1 into 4 power 1 or 2 cube you take it, right. So, it becomes 2 cube. Now, it is not a square factor for k equal to 3, therefore, minus 1 whole power 3 equal to minus 1 so it is actually square factor means 2 square into 2. So, it is a multiplicative, therefore, one of the term equal to 0, therefore, 0 net value is 0. So, very careful to do that. For one square term comes under a multiplicative, it becomes 0. For n equal to 9, we have a 3 square, it becomes 0. For n equal to 10, 5 into 2, therefore, 2 factors, therefore, minus 1 whole power 2 equal to plus 1, therefore, plus 1. So, like that you have to do the Mobius function. So, it follows with the theorem, if mu of n be the Mobius function, then mu of n is a multiplicative for GCD of m comma n equal to 1. Therefore, mu of m n equal to mu of m into mu of n, and let nu of n equal to summation d divides n mu of d, and then nu of n equal to 1 if n equal to 1, and then if n is greater than 1 it becomes 0. So, that is the meaning of Mobius function corresponding to new function n of n. So, what are all the divisors of n, that you have to take it, so that it will come. So, the proof is, if either p square divides m or p square divides n and p is a prime, obviously p square divides m n, hence the mu of m n equal to 0, which is equal to mu of m into mu of n is trivial. So, both m and n are square free integers. Say m equal to product of primes, n is equal to another product of primes, then mu of m n equal to mu of p1 into p2 into ps into qs, q1 into q2 into qt, therefore, minus 1 whole power s plus t, which is equal to minus 1 whole power s into minus 1 whole power t, therefore, mu of m into mu of n. If n equal to 1, then nu of n equal to summation d divides n nu of d, which is equal to mu of n equal to 1 if n is greater than 1. So, we need only to evaluate nu on prime powers. In addition, nu of p power alpha equal to summation d divides p power alpha, which is equal to mu of n into mu of plus mu of p square and so on, mu of p power alpha, mu of n is 1, this is minus 1, this is 0 and so on. So, net value is 0, therefore, nu of n equal to 0 for any positive integer n greater than 1. So, the Mobius inversion function is, if f is any arithmetic function, if g of n equal to summation d divides n f of d, then f of n equal to summation d divides n mu of n by d into g of t, which is equal to mu of t into g of n by d. So, if f is a arithmetic function, then g of n equal to summation d divides n f of d. Therefore, we can split it into 2 and summation d divides mu of d. Already g of n is summation d divides n f of d. Therefore, apply here, so that d divides n by d is f of d, and the sum is taken common, mu of d into f of a, and we can return as f of a into mu of d, and we can write summation d divides f of a and mu of d, and this value is 1 and f of this value is f of 1, therefore, f of n. So, the converse of the Mobius inversion is f of n equal to summation d divides n mu of n by d into g of t, then g of n equal to summation d divides n f of d. So, note that the function tau and sigma are the value of tau of n equal to summation d divides n 1, sigma of n equal to summation d divides n d. So, invert to give one can be expressed as summation d divides n mu of n by d into tau of t, and n can be expressed as mu of n by d into sigma of d. Therefore, the relation between Euler phi function and Mobius function given in the following when n is greater than or equal to 1. So, based on this we have to investigate the occurrence of prime numbers among the positive integers. The following some counting result of the number of the primes, each numbered positive integer from 1 to 1000 contain respectively the following numbers of the primes. So, 1 to 1000 we have 25 is corresponding number of primes, 21, 1 to 100, and then 200 to 300, like that you have to count it, so that we have the resultant of number of primes in between the each 1 to 100 25, 100 to 200 is 21, and 300 to 400, 400 to 500, 500 to 600, like that. These are all the things we can easily count it. And for 100 from 10 power 6 to 10 power 6 plus 1000, the corresponding sequence are 6, 10, 8, 8, 7, 7, 10, 5, 6, 8. So, like that for each 100 from 10 power 7 to 10 power 7 plus 1000, the corresponding sequence are 2, 6, 6, 5, 4, 7, 10, 9, 6. So, like that each numbers of the corresponding sequence we can design. So, these are all the distribution function of pi of x. So, except 2 and 3, any two consecutive primes must have the distance that is at least equal to 2 pairs of primes with the shortest distance of the called twin primes. Of positive integer less than or equal to n, there are 8 twin primes, 3 and 5 you take it, 5 and 7. So, these are all twin primes, 11 and 13 and see 17 and 19, 29 and 31, 41, 43, 59, 61, 71, 73, they are twin primes. So, based on this we have a statement, if x be a positive real number greater than 1, then pi of x defined by summation, or what are all the primes less than or equal to x that you have to collect, that is called it as pi of x. So, the number of primes less than or equal to x, it is also called prime counting function or prime distribution function. For example, the prime numbers up to 100 are 2, 3, 5, 7, 11, 13, 17 prime, 19 prime, 23 prime, 29 prime, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97, all are primes. Now, you calculate pi of 1. How many pi of 1? Nothing is there, therefore 0. You take pi of 2. How many primes? Only one number, 2, 1. And phi of 3, yes, 1 and 2, therefore phi of 3 equal to 2. Phi of 10 you take it. So, 1 is prime, 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime, total is 4 numbers. 20 you take it 8. So, phi of 30 10, phi of 40 12, phi of 50 15, phi of 75 21 numbers, phi of 100 25 numbers. So, like that we can calculate how many prime distribution function between the number from one number to the another. So, this is the numerical values of the ratio. If you take phi of x by x, when x tends to infinity, it becomes 0. Therefore, we have a table of x equal to 10, phi of 10 we have a 4, and then if you divide it, it becomes 0.4. 10 square mean 100, phi of 100 is 25 numbers or primes there, and if you take the ratio, it becomes 0.25, like that. If approximately it goes, all the values are converted nearer to 0. Therefore, that is the meaning of what? When limit extends to infinity, phi of x by x equal to 0. So, this way we can calculate that prime distribution among one number to the another number. So, there ends the prime distribution.